So in this problem, we've got a mass of 5 kilograms of liquid and vapor. They're in equilibrium. They're in a piston-cylinder device, and the piston has a weight. When the piston moves, it induces a pressure of 300 kilopascal, and that's just because of the weight of the piston pushing down on the air. Heat is added to the system, and we've got 2 kilograms of liquid water. Therefore, we've got 3 kilograms of water vapor. So heat's added. Once the pressure reaches 300 kilopascal, the piston moves upward at that point. And heat transfer continues until the volume is 20% greater than the original volume. And the first thing we want to do is draw this state transition on a PV diagram. Try to draw your own isotherms on this PV diagram. And when I do it, I often screw it up, but I'll draw a temperature like this. And I've drawn it wrong. I can tell at a glance because when I compress a liquid, if I squeeze on it and I decrease its volume, I would expect the pressure to shoot up rapidly. So this pressure is going down, and I drew it wrong. So here are correctly drawn isotherms. I've drawn it for 3 different temperatures. So we want to draw the state transition on this PV diagram. And there's 2 things that occur. The first is heating under constant volume before the piston is able to rise. And then the second one is heating at constant pressure. So at constant volume, the state transition can only move vertically, but at constant pressure, it can only move horizontally. So in the initial state, we've got some vertical transition, but what we don't know is, at this fixed volume, is it heated to beyond the two-phase region? So did we boil all the water into steam or not? And it turns out that we will, and I'll show you in a second how we can figure that out. Once the pressure is great enough, the piston lifts up, and we continue at constant pressure to a greater specific volume. So here's the state transition on a PV diagram. So we've drawn the state transition. We want to determine the initial and the final temperature. And to solve these problems, in both states, I compile a list of all the intensive variables that I know. So for example, at state 1, I know that the pressure is 125 kilopascal. And because it's a two-phase mixture in equilibrium, I can look up in the water table the initial temperature. So here's the pressure table for saturated water. At this pressure, I find a saturation temperature of 105.97 degrees C. And for state 2, all I know is that P2 is equal to 300 kilopascal. And I can't tell you anything about the temperature because I don't know what isotherm I'm encountering here. Or we would expect that there is some other isotherm that this would intersect, but we don't know how far to the right this arrow is going or what isotherm it lands on. I should point out, within the two-phase envelope, you can specify either the pressure or the temperature, but you're not allowed to specify both. So state 2, the only intensive variable that we know is that P2 is equal to 300 kilopascal. One thing I do know is that the total mass in state 1 is equal to 5 kilograms. And that means the total mass in state 2, because it's a closed system, is also equal to 5 kilograms. Another thing that we know is that the volume at state 2 is equal to 1.2 times the volume at state 1. So if I knew the volume at state 1, I would know the volume at state 2, and then I could find the specific volume at state 2, because it's simply the actual volume at 2 divided by the total mass in the system, which we know. And if I can get V2, that gives me another intensive variable to work with. So in state 1, because I do know the pressure associated with it, I can find the total volume. I simply take the mass of vapor, multiply that by its specific volume, and add that to the mass of fluid and multiply that by its specific volume. So in terms of an equation, the actual volume at state 1 looks like this. And I can look up the specific volume of the liquid and the vapor up in the saturated water table. And at a pressure of 125 kilopascal, the specific volume for the saturated liquid of 0.001 cubic meters per kilogram, and a saturated volume for the vapor of 1.3750 cubic meters per kilogram. And what I come up with when I plug in numbers is 4.127 cubic meters, and that's the volume at the initial state. So that's the total volume of the liquid and the vapor beneath this piston before it starts rising. And V2 is 20% bigger, so what I get for V2 is 4.953 cubic meters. So now I can find the specific volume at the second state, and I get a value of 0.9905 cubic meters per kilogram. Let's try to determine the mass of liquid water that's remaining within here once the piston first starts moving. So the way I've drawn this PV diagram, the temperature rose, and it rose until it was outside the two-phase region. So this diagram would suggest that all of the water had boiled off before the piston started moving upward. So we'll try to confirm that. And one way we can do so is we know the pressure. Let's figure out what the specific volume of the vapor would be in this case. And if the specific volume of a saturated vapor at this pressure is less than the actual volume, or in other words, if the actual volume was bigger than the specific volume associated with a saturated liquid, that means it's now a superheated vapor because we've moved to the right of the saturated vapor line. When the piston first starts moving, we know the volume, we know the mass. We can calculate a specific volume of 0.825 cubic meters per kilogram. So when the piston first starts moving, we have a specific volume, 0.825 cubic meters per kilogram, and a pressure of 300 kilopascal. So we want to figure out, is this specific volume, is it greater than the specific volume of saturated vapor? So we come back to the saturated water, the pressure table, and we'll look for a pressure of 300 kilopascal, and this column here is the saturated vapor column. So let's scroll down till we hit 300 kilopascal. And the specific volume of the saturated vapor in this case is about 0.6 cubic meters per kilogram. Before the piston even starts moving, our specific volume is bigger than the specific volume of the saturated vapor. So that means before it even starts moving, the system is in a superheated vapor condition. So to answer the question, how much water is remaining? In that case, there is no liquid water remaining once the piston first starts moving. So what we've got left to find is the final temperature and the amount of work done. So let's think about the final temperature. We know we're in the superheated vapor region, and we know there's a pressure, and what else do we know at state 2? We've got P2 is 300 kilopascal, and the specific volume at state 2 is 0.9905. So we know two intensive variables, and that is enough in the superheated region to give us any other information that we're interested in, including what we want in this case, which is the temperature. So here's the superheated water table, and we're at a pressure of 300 kilopascal, or 0.3 megapascal. And for each specific volume, we can back out a temperature. And this first column is the specific volume, and we want a specific volume of about 0.99. So we're going to be somewhere between a specific volume of 0.87 and 1.03. The first one corresponds to a temperature of 300 degrees C, and the second one corresponds to a temperature of 400 degrees C. We expect to get a temperature between 3 and 400 once we interpolate. So here's a general formula for linear interpolation. Plugging in numbers, I come up with a temperature of about 374 degrees C. So this is the final temperature in the system. The only thing we have left to calculate is the amount of work that was done in lifting up this piston. And it's important to recognize that no work was done initially because the volume was fixed. There was no flow work. The only time the work was done was when the volume increased 20% when the piston was lifted. So the boundary work is the integral of P dV. In this case, the pressure is constant, so it comes out. We're left with P delta V, and the pressure is 300 kilopascal, or 300,000 pascal, times delta V, which is the volume at state 2, which we calculated, minus V1. And what we come up with is a value of 248 kilojoules.